Hello everybody, and welcome to the video on the algebra and trig connection. In my opinion, this video starts the fun of starting to solve puzzles, hence why I have puzzle pieces here. When we're doing trig identities, what we're really doing is looking at a puzzle and thinking about all the different ways that we can solve it. And not only is it a puzzle, this connection should be a big deal. This is when we're combining something that we know with something new. Over the next few videos, I want you to have that aha moment. And when I see algebra and trig together, this is what I hear. It's an absolute delight. It's just the time where you start to make those connections. Now, for those of you who don't know, I was very much involved in choir in high school and college, so that was amazing to me. And that's what I see when I see algebra and trig together. It's just amazing, heavenly, just a true delight. So with that said, let's move on to some examples so you can start seeing in this video and the next videos what connections you can see. So if we start with simplifying this first expression, what this really is just combining like terms. If we have 1w plus 1w, in the past you would have just said, well, that means I have two w's. Not w squared because we're not multiplying, we're adding. In a similar way, when we connect this with trig, if I have one cotangent x plus another one cotangent x, we must have two cotangent x's left over. So one method we could use for a connection is combining like terms. Here's a good example. Katie simplified the following expression and found an answer of x minus w. Do you agree or disagree, and why? So please pause the video for a minute, think about this, and write down if you agree or disagree. So please pause now. I wholeheartedly disagree with Katie. She did not follow the order of operations, and what she did was she illegally crossed out the y's without considering that there is a minus sign here. Now, before we get to this problem, let me put one in here with just numbers. Something like 6 times 4 minus 2 divided by 4. Notice that I picked the same value for y and y. If I were to do the order of operations on this problem, the first thing I would have to do is simplify on the top, then the bottom, then actually divide, because a big division bar is a grouping symbol. So if I did this with the order of operations, I would get 24 minus 2 on the top divided by 4, which would be 22 divided by 4, which would reduce to 11 halves. Now, if I broke the order of operations and I just decided to cross out the 4's like this, I would get 6 minus 2, which is 4, which is not even close to 11 halves. So this right here is mathematically illegal. What we can do legally, though, is we can think about that the y is dividing both of these entities. So we can split this up from one fraction to two fractions. And this is going to be a common theme in this video. We can think of this as xy over y minus w over y. When you cross out the 4's or cross out the y's without thinking about the minus sign, you're forgetting that this y also has to be dividing the w. So the actual answer to this problem would be this. Now that they're separate, you can cancel the y's. So it would be x minus w over y. That is the true simplified answer. So please be careful of that as we keep going. This is the problem we just did. What we did legally is we split this over into two fractions. Now legally crossed out the y's and got x minus w over y. The reason the puzzle piece is here is, again, it's an algebra connection to trigonometry. So if I looked at this problem and I didn't know how to simplify it, I see a subtraction sign, could be an addition sign, over a single number or a single trig function. I can go from one trig function with a fraction to two separate fractions. 1 over tangent of x. Now that I have legally split it from 1 to 2 fractions, now the tangent x is crossed out, so I'm left with sine x minus 1 over tangent of x. Now I want to remind you at this point that we want to try to simplify this as much as possible, which is why it's a puzzle. Now let me go back to the previous video that I made, and I want to remind you that 1 over tangent of x is really the same as cotangent of x, or cotangent of theta. So I can even simplify this more to be sine of x minus cotangent of x. If we can get rid of fractions, that's amazing. This example, this in my opinion uses exponent rules. What you did in your Algebra 1 and Algebra 2 courses was thought about if it had the same base and you have a power of 2 on the top and power of 1 on the bottom, you could subtract the exponents, or you could think of it as x times x on the top, 1x on the bottom, and then legally cross out a pair of x's. And in this example, we have one pair of x's we could cross out, so this just becomes y, and this example just became x. Now notice, unlike the last examples here, we did not, or these two, we had a plus or a minus sign in the way. These examples, we do not have a plus or a minus sign, so we're legally allowed to cross things out. If I look at my trig connection or my puzzle, I have cosine squared x over cosine. You could think of it as subtracting one cosine from two of them, or you could even write it as cosine of x times another cosine of x over cosine of x, cross out a pair, and you're left with just cosine of x. This example, if you don't see any plus or minus signs, you're legally allowed to cross out what's in common, so this example is also just cosine of a variable, which that looks like a very strange W, but that's a W. This next example I would like you to try on your own based on what we did on this example here. So I would like you to please pause your video and try the algebra and trig connection on your own. Please pause now. So I want to check back in with you briefly about the algebra. If you correctly simplified this by making it from one fraction to two, because both the x and the y are dividing by x, I agree with you. Just make sure this was your final answer. X divided by x, or any number divided by itself, is always 1. So this ended up being 1 plus y over x. I'm going to pause again. With that idea, I would like you to try the trig. Please pause now. Here's my answer for the trig connection. I had changes from one fraction to 2. Both of them had a denominator of sine of x. These canceled out to be 1. Then I got 1 over sine of the x, which from the identities from the last video, I know that if I have 1 over sine, that is the same as the reciprocal function of cosecant. Factor the following. So if I think about my factoring skills, I want to try to split this into two parentheses. What times what gives me 4, and what times what gives me x squared, and they need to combine to be a 0x in the middle. Well, let's try. 2 times 2, x times x. If I want this 2x and this 2x to cancel out and become 0, I need one of them to be positive and one of them to be negative. So this is the proper factoring for the algebra relationship. If I transition this idea to trigonometry with the same numbers, even though I have a trig function, I can still treat it the same way. I still need a middle term of 0. Technically, it'd be a middle term of 0 tangents. So let me try this. 2 times 2 is 4. Tangent of x times itself is tangent squared. If I have one of the two tangent x's being positive and one of them being negative, the middle terms would cross out to be 0. Let me show you. If I actually went backwards, this is my answer, but if I actually multiplied this out or FOILed it, we would get back to this. So that would be 4 minus 2 tangent of x plus 2 tangent of x minus tangent squared x. These middle terms would cross out, and so I'd end up back where I was at the beginning. So this is definitely my answer. If I gave you something like this, now the common acronym is FOIL, but I sometimes just prefer the directions of distribute, because what you're really doing is first distributing the y to both terms, and then you're distributing the -2 to both terms. So I would like you to pause the video and multiply that on your own, and please come back and check your answer. Here's my answer based on color coding, distributing the first, distributing the second, and combining like terms. If I apply the same idea with trigonometry, so if I gave something like this to you, which looks a little bit more confusing, think of it as a binomial times a binomial. So the first thing I'd have to distribute is the sine of y. So sine of y times sine of y is sine squared of y. Sine of y times 3 is 3 sine y. If I now distribute the negative 2, that would be negative 2 sine y's minus 6. I then notice that both of these are like terms because they're both just plain sines. This is not a like term because this sine is squared. So my final answer would be sine squared y plus 1 sine y minus 6, which is the same answer as above, but instead of y's, we have sines. And this could work with any trig function, cotangent, tangent, cosine, secant, anything. Expand the following. This is a very common algebra mistake. When students look at this, they think it's just x squared times y squared. But remember that when you square something, it's something times itself. So it's really x plus y times itself. And at this point, it's a binomial times a binomial. So again, what we're really doing is just distributing. X times x is x squared. X times y is xy. Y times x is still just xy if you think about it alphabetically. And then y times y is y squared. So this final answer, you can combine these like terms, and there's a 1 technically in front of both. So we'd have x squared plus 2 xy terms plus y squared. A good reminder for algebra, by the way, is remember you're allowed to multiply anything you'd want. We're allowed to multiply x times y, that's perfectly fine, but we're not allowed to add x's and y's because they're not like terms. So keep in the back of your head that multiplying, you generally have a lot more freedom than adding or subtracting. With that said, I would like you to think of this problem as sine of x plus cosine of x times itself, sine of x plus cosine of x. I would like you to get a head start on me here. So I would like you to get as far as you can multiplying these two, and I'll be back with you in a bit. So please pause now. All right, so here's what I've done so far. I distributed the sine of x to both terms and got sine squared x plus sine x times cosine x. I then distributed the cosine x to both terms and got cosine x sine x times cosine squared x. In red, the only thing I did was switch the order of this term. And you don't have to do this if you see this, but I want to remind you that when you multiply, it doesn't matter what order you do this. So 3 times 2 is the same as 2 times 3. So these two things are really like terms. So there are 2 sine x cosine x's. There is still a cosine squared x in the back, and there is a sine squared x in the front. Now it seems like we can't do anything else because we don't have like terms. Well, we definitely can't combine like terms, but I do see something. I notice I have a sine squared x and a cosine squared x. So I'd like to bring you back to the video that we did yesterday. Do you remember the Pythagorean identities, that sine squared theta plus cosine squared theta equals 1, or sine squared x plus cosine squared x equals 1? So these two things together should equal 1. So if I go back to this, I have sine squared plus cosine squared. These two together really just equal 1. So I have these can be replaced with just 1 plus 2 sine x cosine x. So this is my final answer for this problem. Now, later on, you will recognize that this in itself is an identity as well, but we're not quite there yet. So let's wait on that. This example, again, I would like you to try this on your own. I would like you to factor this one first using your algebra skills, and then see if you can go from algebra to trigonometry and apply it twice. So please pause the video now. Just to check in with you, I got this to factor to be x plus 1 times another x plus 1. So you could really write that, the most simplified as x plus 1 quantity squared. So please use that logic on the trig one. Please pause now. Based on the logic above, my final answer for this is in this green box. If you have any questions about it, please feel free to ask in class. So next I'd like you to read this question and write down if you think his answer is reasonable or unreasonable. Feel free to use plug-in numbers and even check. So please pause now, and I will be back with my answer. Here are a few things I wrote down. Feel free to pause your video and write down what you like from this or what would help you when you look back at your notes. So please pause now and write what you'd like. And here's a final thought to leave you with.